In this lesson, we're going to talk about simplifying our model. And that's because all else equal, simpler models are preferable to complex ones. Remember the Zen of Python? Simple is better than complex, and complex is better than complicated. And this doesn't just apply to programming. The same thing can be said about our regression model. By the way, you can always bring up this little gem of programming philosophy when you type import this in Jupyter Notebook. Simple models really are preferable to complex ones, all else equal. So the question is, how can we simplify our model? One of the easiest ways is to remove some of the explanatory variables. But can we just drop some features? Is that a wise thing to do? And if so, which features should we drop? What about the features that were not highly correlated with property prices? In the correlation matrix, we saw that distance from employment centers only had a 0.25 correlation with our target. DIS had a low correlation with price, but also it had a high correlation with our industry factor of minus 0.71. At the time, we were wondering how much value the distance from employment centers feature really added. But now we know. Scrolling down, we've got the p-values which test for the significance of our different factors. And we can see that distance is actually very statistically significant. So we should probably keep DIS around. Now, on the other hand, looking back up at our industry factor, this has a p-value of around 0.44, meaning it is not statistically significant. The threshold for p-values, if you recall, was 0.05. So now the question is, should we try removing the industry factor from the model? And the thing is, it is really tempting to remove insignificant predictors. But even dropping statistically insignificant features is not something people do lightly, because even a feature with a low p-value can add value to the model as a whole by providing some kind of information that the other features do not provide. Actually deciding on what to keep and what to throw away from a machine learning model is a bit of an art. And it gets into this whole topic of feature selection, which is a very big topic indeed, and one that we will continue to tackle throughout this course. The goal of this lesson is to introduce you to this topic of feature selection in the context of a regression model. And we will be looking at a metric that you can use to help you make your decisions. And that metric is called the Bayesian Information Criterion, or BIC. The Bayesian Information Criterion is a way you can measure complexity. It's basically a number that allows you to compare two different models. So what you end up doing is you run a regression with model number 1, and then you run a regression with model number 2. Now, model number 1 might have a big value of 148, and model number 2 might have a big value of 154. The actual number doesn't by itself mean very much. What matters is which one is lower, because all else equal, a lower big number is better. So this measure can help you pick between two or more models. So what models will we compare? Well, for starters, let's compare the model that includes the industry feature and the model that excludes the industry feature. Let's commemorate this with another markup cell in Jupyter Notebook. So I'm going to change my cell here to Markdown and then put a section heading here, model, simplification, and the Bayesian Information Criterion. To calculate the Bayesian Information Criterion, we're once again going to use our stats model module's regression capabilities instead of scikit-learn. So let's copy the cell here and paste it below. I'm going to delete these comments and I'm going to add a new comment up here that reads original model with log prices and all features. And the data frame that I've got here, I'm going to store inside a variable. So I'm going to say original underscore coef is equal to pd.dataframe and so on. And now what I want to do is I want to add some additional print statements. And in these print statements, we'll output both the Bayesian information criterion value and the R-squared for the regression. Now, previously we've used scikit-learn score method to print out the R-squared, but things work a little differently with the stats model module. And I think this is a good time to practice making sense of the official documentation. So as a challenge, can you look up the stats model docs for the regression results and figure out how to print out both the Bayesian information criterion value for this regression as well as the R-squared? I'll give you a few seconds to pause the video and give this a shot. You ready? Here's the solution. Being able to read and interpret the official documentation for a lot of these Python modules is one of the key skills in becoming a better programmer. If I click on my results object and press Shift-Tab on my keyboard to bring up the quick documentation, I don't actually get anything useful. I just see that to get further information, I need to look at the regression results documentation. The same thing is true if I click here and I find out that I'm just dealing with a data frame, or when I click here. So in all these cases, the quick documentation isn't actually helping me all that much. I'm just not having any luck on getting the relevant information. So what I'm going to have to do is I'm going to have to Google the documentation myself. The best keywords to enter into that white text box are stats model, regression, results. And that should pretty much take you to one of the stats model pages. Now, out of these three that I've got here, the one I'm looking for is the page for the documentation on the regression results object. So it's the third one down here. This is the regression results object from the linear model. This is the documentation page that you want to be looking for. The other reason why the regression results page that I've clicked on is the relevant one is because this particular object, the regression results wrapper, inherits most of the methods and attributes from regression results, meaning the capabilities of a regression results wrapper object, which we've got, and a regression results object are pretty much the same. They have a lot in common. A lot of the methods and attributes are inherited from this particular object. Yeah, they're closely linked. So this is why I'm looking on this page. Now this is an incredibly long page if you look at it. It's very, very comprehensive. But the interesting thing is that we can find both the params attribute and the p-values attribute on this page. So if I search for params on this page, I can find params listed as one of the attributes, and I can also find p-values listed as one of the attributes. And you probably already spotted it. At the top of the page is the BIC attribute, the Bayes information criteria. So BIC is the name of the attribute for the Bayes information criteria. And the way we access this attribute is simply by writing results.bic. And if I hit Shift Enter, I can see what the value of this actually is. It's negative 139.85. So about negative 140. And what about the R-squared? Going back to the documentation and scrolling down, R-squared, unsurprisingly, has the attribute name R-squared, all lowercase and in one word. So results.R-squared will bring up the R-squared for this regression, which is 0.793. Let's wrap both of these lines of code in a print statement. So I'm going to have print BIC is the end of single quotes, comma, results.bic BIC, closing parenthesis, and then I'll have print r squared is, comma, results.r squared, closing parenthesis. There we go. Okay, so now we have both the r squared and our BIC printed out. The comforting thing to see is that the stats model and scikit-learn give us exactly the same r squared, so we're doing things right. Now in this case, the Bayesian information criterion is actually a negative number, and that's absolutely fine. What matters is how this number stacks up to our next model. So I'm going to copy this, paste it, and then I'm going to modify my comment. I'm going to write here, reduced model, number 1, excluding indus. And then what I'll say is that x underscore including underscore constant is equal to x underscore including constant dot drop, parentheses, square brackets, single quotes, indus, all caps, comma, axis equals 1. So in this line of code, I'm redefining the data frame of features by overwriting what's stored inside this variable. I'm dropping the indus column from the data frame and storing that as the new feature data frame. So on this line, when it comes to training our model, we are excluding the indus feature. Next, I'm going to change the name of this variable to coef underscore minus underscore indus. So that way we're not overwriting the coefficient data frame from the cell above. And I'm going to delete this comment here. Now let me hit Shift Enter and refresh this cell. So this result is already quite interesting. What we can see is that our Bayesian information criterion has gotten more negative. We've now got the value minus 145.2. So this is an even lower number than before. So we have an improvement in terms of reducing complexity. But at the same time, it's also really nice to see that the r squared at 0.79 pretty much stays where it is. So even though we have removed one feature from our dataset, it hasn't really impacted our fit in a material way. This is actually very encouraging. Let's go back up to our p-values and experiment with removing something else. Let's experiment with removing age. Coming back down, I'm going to copy the cell, paste it, change my comment here to reduced model number 2, excluding indus and age. And then in this line, I'm going to have to add the single quotes and age between the square brackets. I'm also going to rename our data frame of coefficients to maybe reduced coef. And now I'm going to hit Shift Enter. And what we actually see is a further improvement based on the Bayesian information criterion. So we get an even lower big number at minus 149.5, but we see no material change in the r squared. So this makes me think that removing both indus and age is actually a beneficial thing. We can probably safely drop these two features, simplifying our model without incurring too much of a cost in terms of lost information and a worse fit. Now, even though I just gave you two examples where removing a feature improved the Bayesian information criterion and left the r-square pretty much unchanged, this isn't always the case. If I change age to one of the other features, say maybe zone, ZN, and press Shift-Enter, what we see is not really all that clear-cut. In this case, we have a higher big number and a lower r-squared than before. So this is probably not the direction we want to go in. Same thing if I change this to our tax feature. Again, we're making our model worse. And same thing if I change this to the LSTAT feature. Removing LSTAT actually makes our model much, much worse. You can see how much the Bayesian information criterion jumped and how much lower our r-squared is in this case. So LSTAT is actually very important to keep in the model. I'm going to change this back to age and press Shift-Enter so that we're back to where we started. Okay, so where are we now? We've made 2 small tweaks to our model. We've removed 2 of the features which were not statistically significant, and we've looked at the Bayesian information criterion and the R-squared to provide additional justification for leaving them out and simplifying our model. And by doing so, we've managed to improve our big number from around -140 to -150. So we get about a 9-10 point improvement in the big number, but we don't incur a material penalty on the R-squared. We're still on 0.79. Cool, so that about wraps up our introduction to thinking about feature selection. And one thing that we can do now is we can link this lesson to our previous one. We can link this to the discussion on multicollinearity and looking for stability in the theta estimates for our features. Because we've made quite a few tweaks to our model, and we said that one of the symptoms of multicollinearity are unstable coefficients. Having run 3 different versions of our regression and having stored our coefficients in some variables, we can now look at them side by side and double check if there are any strange developments. Now, I'd be surprised if we saw any because we have no indication of multicollinearity so far. But take a look at this. If I create a variable called frames and make that equal to a list of our data frames. So we had the original coefficient, we had the coef underscore minus underscore indus data frame, and then finally we had the reduced underscore coef data frame of coefficients. To put them all side by side, I'm going to use pandas concat method. So pd dot concat, and then in the parentheses, I'm going to provide my list of data frames and an axis. So I want this to be concatenated along the columns, so side by side as opposed to top to bottom, right? So axis is going to be equal to 1 instead of 0. Let's see what we get. Fantastic. Now, what you can also see here in this table here is how Python treats missing values in a data frame. You see these nans, N-A-N? Nan stands for not a number, meaning there's a missing value here. So this column here is our reduced model without the age and without the industry feature. So we've got nans in place of these rows. Looking at this table is actually very, very encouraging because what I'm seeing is that despite tweaking the model, all the coefficients, for all 3, so like Charles River, crime, they all are remarkably consistent. So the numbers change somewhat, but they don't switch signs, they don't change drastically. So these are all very, very stable coefficient estimates. And the same actually holds true if you were to remove tax, which we suspected was a potential problem source. So even removing tax and rerunning this, you'd see that the theta estimates are nice and stable between the 3 models. And that brings us to the end of this lesson. In the next one, we're going to take our evaluation of our regression even further. We're going to look at how far off our model's predictions were from their true values. We're going to be looking and analyzing our regression residuals. Now, as an aside, while putting this lesson together for you, I found myself Googling the word big and trying to read up on the information criterion. And for a split second, I was quite confused why all I got on the front page was information about pens and the website of the Bournemouth International Centre. The other time that happened to me was when I read up on nested tables and I was kind of confronted with this. So yeah, if you have any stories like this to share, please put them in the comment section for this video. I'd love to hear it. I'll see you in the next lesson.